Hello, welcome to this refresher course on positive matrices and an economic model, actually a model by Leontiev. My name is Ralf Schill. I'm professor at the University of Dresden in Germany and also part of the faculty of the University of Delhi. I want to present some, hopefully, basic things on matrices, but also on positive matrices, and to show where they can, for example, be applied. I may mention also at the end where this theory of positivity can also be applied in different contexts. So we are considering matrices, real matrices actually, but for spectral theory, as you might know, when we speak of the spectrum of a matrix, it is better to let it act on Cn. So Cn, first of all, C is the set of complex numbers, and Cn, that's a vector space, complex vector space, here over the field of complex numbers. It is, for us, for doing analysis, also equipped with an inner product. And we take here a special inner product, the Euclidean inner product. Which I write in this form. So here, for two vectors x and y, two complex vectors, the inner product is xi yi bar, and here I sum from 1 to n, and xi and yi are the components of the vectors x and y. So here x is equal to this vector, and also y, they are both in Cn. With an inner product, we also get a norm and an Euclidean distance. This allows us to do analysis. We have the notion of convergence in this vector space, continuity, and especially here continuity of linear mappings, but actually all linear mappings from this vector space into itself are actually continuous. Nevertheless, it might be good to have this inner product here. So this gives a topology or metric on Cn. But we will use one more structure of the space, and so that's a third point. It's not only a vector space, but Cn is an ordered vector space. So we have, like in the set of real numbers, the notion of positivity. But I have to explain in which sense I use positivity, because sometimes this is not unique in the literature. So a vector x is greater or equal to 0, a vector, and we say x is positive. Some people use here non-negative. If all components are greater or equal to 0, and the components are actually complex numbers, but this means also that actually the components are real numbers, so the vector is in all components just real, and all components, these real numbers, are greater or equal to 0. And this holds for every component. We might also need this notion of strict positivity. I call it here strictly positive. And some people in literature use here only positive and say here non-negative, but I define it in this way. If all components are strictly positive, strictly greater than 0, and here again for all I between 1 and n. So we see this vector space with two more structures, a topology and here an order, and we can define the set of all positive vectors. That's the positive cone. So in R2 it would be one quadrant of all vectors where the first and the second component are greater or equal to 0. So the cone is a closed subset of the space here. And on Cn we consider matrices or linear mappings, but here we take matrices. That's a complex matrix. And we say here the components, we write it as Aij, and here A, I, and J are between 1 and n. So these are the components of the matrix. And there's a one-to-one correspondence between matrices and linear mappings from Cn to Cn, just by choosing a basis in Cn, and usually you choose the standard basis of canonical unit vectors, which are everywhere 0, just in one component they are 1. And once you have a basis, you can represent every linear mapping by a matrix, or when you have a matrix, you can define a linear mapping. Every complex matrix the spectrum of A is the set of lambda in C. Lambda is an eigenvalue of A. This is called the spectrum of A. And you should know that every complex matrix has up to n different eigenvalues. So here in the complex plane, so this is the complex plane, we have here a real part of lambda and the imaginary part of lambda. And in this complex plane we may have a few eigenvalues, and maybe here's also a real eigenvalue. What is interesting outside the spectrum, so eigenvalue actually means that lambda times identity minus A is not invertible, or there is a vector such that a vector which is non-zero, such that A times this vector is equal to lambda times this vector, just a multiple. So outside the spectrum, actually lambda times identity minus A is invertible, and so if lambda is not in the spectrum, then lambda times identity, and I write it shortly like this. I don't write the identity. Lambda times the identity matrix minus A is invertible. And for every lambda outside the spectrum, so here this is a finite set. And outside we have this resolvent, so the inverse lambda is called resolvent for every lambda outside the spectrum. We have a resolvent. Sometimes we call also resolvent the whole function which is defined on the complex numbers minus the spectrum, and this function is actually an analytic function. It is it can be developed in power series locally. At every point we can develop this function of lambda in a power series in lambda at a certain point. Let's call it mu. Let me recall one special series, which in the case of real numbers is the geometric series. So if the norm of this matrix is less than 1, and here the norm is the supremum of all AX norm, where X has norm 1 or less than 1, then the identity matrix minus A is invertible, and the inverse, well, if A would be a number, you would have here 1 minus A inverse, or 1 divided by 1 minus A. This is given by the geometric series, which for matrices is sometimes also called the Neumann series. So the series here from k equals 0 to infinity, A power of k. And actually, this condition here means that the norm of A is less than 1, but actually the norm of this power here is estimated from above by the norm of A to the power k, and this gives us, since this is less than 1, that this series here converges absolutely in the space of matrices in Cn times n, and it gives us the inverse here. Yes, and in particular, for arbitrary A, so and lambda greater than the norm of this matrix, actually lambda minus A is invertible, and the inverse, this can be calculated by this series here, geometric series. Or von Neumann series. This can be calculated using this von Neumann series. You can factor out lambda, and then you have here, when you factor out and you have here -1, you have a 1 over lambda, and it remains identity minus a over lambda, but a over lambda has norm less than 1, and here we have, so a to the power k divided by lambda to the power k, and here the series from 0 to infinity. So it means that, again I draw here a complex plane. We have here some number which is the norm of A, and we have a circle of this radius. Oh, maybe not very nice circle here. And outside the circle, lambda minus A is always invertible, so the spectrum is inside the circle. And so we obtain that the spectrum is contained inside the circle, and now I define, maybe I should not have put this here, but okay, maybe the absolute value here of this eigenvalue is larger. Actually, we have a second circle okay. So I choose the smallest circle which contains the spectrum, and here we have a circle of radius r of A. So r of A is the supremum of all absolute values of lambda, where lambda is in the spectrum. Is called spectral radius. And this for Neumann series argument gives us that the spectral radius is smaller or equal to the norm of A, which is this quantity here. And actually, now if I would replace here the norm of A by the spectral radius, then for every lambda greater than the spectral radius, just by definition, this here is invertible. But actually, even for those lambda, this series here converges absolutely. That's an argument using complex function theory, which I will not explain here. So, okay, we have a resolvent function outside the spectrum. This resolvent function certainly exists outside this disk here, the greater disk or the smaller disk. They may coincide. And even this resolvent function exists also in this region here, not in the eigenvalues. In the eigenvalues, actually, the resolvent function here only has poles, which means if I write down a Laurent expansion in the eigenvalues, then this Laurent expansion is not a series from minus infinity to infinity, but it starts at some negative value at minus k0, so to infinity, and then if the coefficient at k0 is non-zero, then we call this the order of the pole. So that's a general theory for arbitrary complex matrices, there's already one simplification if our matrix, even if it is acting on the complex space, but it may also act on the real space, if the matrix only has real entries, then it turns out that if lambda is an eigenvalue of the matrix, then also the complex conjugate is an eigenvalue. So in that case, whenever you have one eigenvalue, the complex conjugate is also an eigenvalue. And if you have here one, you have also here one, and maybe you have also a real eigenvalue. It seems I always draw here 5 eigenvalues. That's, of course, depending on dimension. But if we are really in dimension 5, we may have 5 different eigenvalues, but here at least we have here 2 complex conjugates, and one is real. In dimension 5, we always have to have one real eigenvalue. That's just because we compute the eigenvalues by some determinant, by some polynomial, the characteristic polynomial, which would have degree 5, and every polynomial of degree 5 with real coefficients has at least one real root. So here the spectrum is invariant under complex conjugation. But as you know, even if we have a real matrix, we might think that it acts only on Rn, but as it comes to spectral theory, it's better to consider it on Cn and to see it as a complex matrix because still the eigenvalues may be complex. And now a matrix A, which is just a real matrix, is positive and I use it also as in the first case here, if all entries are greater or equal to 0, and here this is now for every I and j between 1 and n. And in this case, we write A is greater or equal to 0, and it is strictly positive if all entries are really greater than 0, all entries. And a matrix, I have defined it in this way, a matrix is actually positive if it is positive and we apply it to a positive vector, then the result is again a positive vector. So positive matrices actually map positive vectors to positive vectors. And this actually characterizes positive matrices. So that would be an alternative definition to positivity here, that Ax is greater or equal to 0 for every x greater than 0. You can easily compute this or verify this equivalence here. So our matrix, when I see it as a linear application, leaves the positive cone invariant. And once we have more structure, we would also expect some more results on, for example, the spectrum of such a matrix. And this is what I want to show next. For the spectrum of positive matrices and also the resolvent function, we can say the following, which I formulate as a theorem. Let A necessarily real matrix be positive. Then we have the following statements. A, the spectral radius, which is just a positive real number, this real number is actually an eigenvalue. It belongs to the spectrum of A. So on the spectral circle, the red circle, there's always at least one eigenvalue, but there's one eigenvalue which is just intersecting with the positive real axis. That's always an eigenvalue, as it is by coincidence drawn here in this picture. There might be other eigenvalues on this spectral circle, also as here in that picture, but since our matrix is real, if I would have another eigenvalue, I would also have the complex conjugate in the spectrum. There exists a positive eigenvector for the eigenvalue R of A. There might be other eigenvectors. I mean, of course, if I have an eigenvector, then also minus this is an eigenvector. But there might also be eigenvectors which change signs. That is, some components are strictly positive, some other may be strictly negative. And the resolvent of the matrix A is positive if and only if the lambda, which appears here, which might be in general a complex number, this is greater than the spectral radius. Let me prove this statement. First, we start with A. For every lambda in the complex plane with the absolute value of lambda greater than the spectral radius, we have lambda minus A inverse. And I take here the absolute value. Even for matrices, I can take absolute values. So our space Cn is not only an ordered space, but okay, this means that just in every component of this matrix, I take the absolute value, and I get a new matrix which is necessarily positive. This matrix here is given by the von Neumann series. So that's A to the power k divided by lambda to the power k plus 1. And here this goes from 0 to infinity. And so this is taken component-wise, this absolute value. And now there's again the triangle inequality. And I would have to take the absolute value of a to the power k, but a to the power k, since a is positive, and there it's actually better to see it in this way, then also a squared and all the powers are positive. So the absolute value of a to the power k is just a to the power k because these are all positive matrices. But here I have to take the absolute value, and then again by the Neumann series, this is actually equal to the resolvent at the point absolute value of lambda. So when we are outside the spectral radius or this circle, then I can estimate the resolvent somewhere outside the circle. So let's say we have here, I can estimate the resolvent here at lambda by, here is the absolute value of lambda, so we are in the same circle, by the resolvent at this point here. And this already shows actually that this matrix here, since it is greater than this matrix, component-wise, that this is a positive matrix. So in some sense, I have already shown a part of C here. So if lambda is real and greater than the spectral radius, then the inverse is positive. We see this here also. I mean, the powers of A are positive, and also here the denominator is positive, and then the sum or the series, the limit here, is a positive matrix. But now we can take now lambda k in C with lambda k converging to a lambda in the spectrum, and the absolute value is greater than the spectral radius. So this one always exists, such a sequence, because by the definition of spectral radius, the spectrum is finite. The supremum is actually a maximum. So this supremum is attained for some lambda in the spectrum. So there's some lambda on this circle with radius r of a, and then we can approach this lambda from outside. So which means that the absolute value of lambda k is larger than the radius, and we can approach it. So here this is converging as k tends to infinity to this spectral value. Shows because every lambda in the spectrum is a pole of the resolvent, so shows so this converges, well, let's say in norm to infinity, but yeah, let's say at least one component converges to infinity. I write it like this. This blows up, but then this inequality shows, and hence the resolvent at this here also blows up, and let's say here in norm, this blows up. So I can also write here the norm. The norm blows up, and then also this norm blows up. That is, the absolute values of lambda k converge to the absolute value of lambda, which is equal to R of A. Yeah. R of A is a pole or singularity of the resolvent. It's a pole of the resolvent. And hence, R of A must be in the spectrum of this matrix. And we have used the positivity here in this inequality. Okay, let me first go to this C before we prove B. So we have already seen for lambda, let me first prove this direction. If lambda is greater than the spectral radius, then the inverse is again by the Neumann series. And this is a series from. So now the matrix A is positive, all powers are positive, lambda is real and actually also positive. So all terms here are positive, then also the limit is positive. So if lambda is greater than the spectral radius, then the inverse is positive. And the other direction, if is positive, then actually lambda must be real because, well, if lambda is, let's say, alpha plus I beta for real part and imaginary part, then, and x is a positive vector, then x is equal to lambda minus A times the inverse x. So this is a positive vector by the assumption. But then A is positive, so actually this here, this is a real matrix. This is in a real vector. And here I have alpha times this positive vector. That's also a real vector. But then I have I beta times this positive vector, and that's complex. But here I know that this result here must be positive, and therefore beta is equal to 0. So the imaginary part is equal to 0. So we already know if the resolvent is positive, then lambda must be real. And let me just finish here, maybe. Now there are two possibilities. Lambda cannot be equal to the spectral radius because the spectral radius is an eigenvalue. If it is larger than the spectral radius, then we are done. And assume now, by contradiction, that lambda is smaller than the spectral radius, and let mu be larger than the spectral radius, then what we actually know is, by assumption, this here is positive. No, we don't use this, but we know that this is from this positive matrix. I subtract again a positive matrix. I already know from the first part here that this resolvent is positive. I subtract it, so I get something smaller component-wise. And here I have the resolvent identity. So that's mu minus lambda times the product of these two inverses. And so this is positive by the first part, this is positive by assumption, and also mu is greater than the spectral radius and lambda smaller, this is also positive, so the result here is positive. But now see, this lower bound is independent of mu, and the upper bound is independent of mu. So and this is independent of mu. This shows that this resolvent here cannot blow up. So this is uniformly bounded for mu greater than the spectral radius, but we already know that the resolvent must blow up in this sense when we approach the spectral radius. And from here we get a contradiction. So it's the uniform bound on this resolvent independently for mu greater than the spectral radius. And this shows that this assumption leads to a contradiction, and therefore this is not possible, remains only lambda greater than the spectral radius. So let us prove the assertion B. So we already know that is an eigenvalue of A by the part A, and therefore a pole of the resolvent, which means that I can write the resolvent, at least for lambda close to the eigenvalue here, I can write it as a series which starts at some minus k0 and goes to infinity, and then there are bk and lambda minus r of a to the power k. So in this sort of power series or restricted Lorentz series, we have an expansion of the resolvent in terms of the series, but the series starts at some negative index here, but finite, and this means that in the series there are some powers of lambda minus r of a with powers which might be negative. And here k0 is greater than 1. There's some, and that's the order, and B of minus k0, that matrix is non-zero, so that's really the order of the pole is k0. So this coefficient is non-zero. Yeah, and therefore when I multiply both sides by this power, for lambda greater than the spectral radius, so I approach the spectral radius, this eigenvalue from the right, then I know that this resolvent is positive, but also here this power is positive, so that's greater than 0. But also I know that when lambda goes to the spectral radius from the right, let's say I write here plus, go from the right, then actually this converges to the corresponding coefficient here, b minus k0, this coefficient which is non-zero and which is a positive matrix. All coefficients here are matrices. Now when I multiply this the left-hand and right-hand side by lambda minus a, so and I let lambda tend to the spectral radius, this is equal to the limit as lambda tends to the spectral radius of well, this is just a very simple limit of the identity function, this continuity, and this here is the limit of this value here, and that's when lambda tends to the spectral radius, that's equal to 0, and hence every vector in the range of this matrix B minus K0 is an eigenvector of A for the eigenvalue R of A. But since this matrix B minus K0 is positive and non-zero, there exists, since B minus K0 is positive and not equal to 0, there exists a positive eigenvector. And I have proved the theorem here above. Okay, so the spectrum is of the following type. The spectral radius here is always an eigen value of the matrix, of the positive matrix. I have here the spectral circle of this radius. And there might be, since our matrix is real, since it's a positive matrix, it is also real, if I have one eigenvalue, I have also another. But I might have more eigenvalues also on the circle, and I might also have other real eigenvalues. So, but the largest, well, on this circle here, this intersection with the positive real axis is always an eigenvalue.